Okay, this second example is a pulley problem where the pulley has mass. Now note, every problem we did first semester with a pulley, we had a massless pulley. So a massless pulley can have the same tension on either sides. Because we don't have to account for the fact that there must be some net torque in order to rotate a pulley with some mass. So if you see massless pulley, you can assume the tension is the same throughout. But as soon as your pulley has mass, in order to rotate something with mass, let's say to the left, all of a sudden now, I have to account for the fact that the net torque has to overcome this moment of inertia. So T1, in this case, if we exert at the same R, has to be greater than T2 so that the disk can rotate. Right? Without a net torque, if the net torque was 0, my angular acceleration would be 0. So this is what's different in a problem with a pulley with mass. So let's see how we can account for this and solve. So we have a frictionless pulley. Frictionless meaning that there's no friction at the point of rotation. So I don't have to account for a torque due to friction while it rotates. Now we have a 0.8 kilogram solid cylinder, which is has a 0.3 meter radius and a rope hanging over it. And we also have to account for the fact that the rope doesn't slip while it rotates. If the rope slips, then we have a kinetic friction scenario, and that gets much more complicated to be able to model mathematically. So we have no slip of the rope. The tension on one side is 12 newtons, tension on the other side is 10 newtons, and we want to find the alpha of the pulley. So let me redraw the picture here. So we have a disk of mass M. It's got radius R, and a rope hangs over the top. It gets pulled on one side with some tension and pulled down on the other side with some tension. And these are different. And we'll say T1 is 12 newtons and T2 is 10 newtons. So because of this, I'm going to have some counterclockwise alpha due to this differential in the tension, providing a net torque about that disk. So we know this is a rotational dynamics problem. We know that we have to figure out the moment of inertia I, which will be based on a disk. So a disk is a solid cylinder. Solid cylinder is a disk. About its center is 1/2 mr squared. So we know that I of the pulley will be 1/2 mr squared. We also know that we have to figure out alpha based upon the net torque. So this becomes a Newton's second law problem where the net torque about the pulley will be I times alpha. Now sometimes you have a pulley problem where you're given some displacement information, like the rope displaces a certain amount and you need to use that to figure out the rotation alpha. But in this case, you don't. So the other thing that I will mention to you guys now, because it will come up, is as this rope accelerates about this pulley, at any given point, it's got some tangential acceleration, and that tangential acceleration is related to R and alpha. And so if the rope doesn't slip, then the rotation of the rope at any given point around this disk is the same as a rotation on the point on the edge of the disk. And we know from previous derivations that the tangential acceleration of something that's got an alpha that's accelerating while it rotates is equal to R times alpha. And this becomes what we call the no-slip condition. because if the rope were to slip, then the rope will be accelerating at a different rate than a point on the edge of the disc. So, but as long as it doesn't slip, this will be true. And where will this become important? This will be important when we need to link the linear world of tangential acceleration. The acceleration of the rope will be, of any point on the rope as it rotates around, will be the acceleration of any other point on the rope as long as the rope isn't stretching, with the angular properties of the rotation of the disc. So that's something that we can use for any pulley problem to relate the linear quantity acceleration tangential to alpha, the rotational acceleration. All right, in this point, we want to find alpha, we need to find I, and we need to find the net torque. So I'm going to bring this down here where we have some room. So the net torque will be the torque exerted by force 1 and the torque exerted by force 2. So if this is my disc of radius r, T1 is going to be exerting a counterclockwise positive torque, I'm going to call plus T1, about the axis of rotation. And T2 will be exerting a negative torque about the axis of rotation. So my net torque, though, will be the positive torque from T1 minus the torque from T2. So that's the sum of my torques. Now that has to equal the moment of inertia times the angular acceleration. Okay, so if I divide by I, I get that alpha will be torque 1 minus torque 2 over the moment of inertia. Well, this is a disk, so I of a disk is 1/2 mr squared, so we're going to substitute that in. And then the torque exerted by force 1 is just the force T1. Now at this point, T1 is perpendicular to R, and T2 is perpendicular to R. So I don't have to find the perpendicular component. I just go out R, down T1, so T1 dot R is going to be my torque exerted by 1, and the torque exerted by tension 2, again this is 90 degrees, will be T2 times R, same radius. So my problem now becomes T1 times R minus T2 times R divided by 1/2, I'm going to sub in for I, 1/2 mr squared, and that equals alpha. So now you notice in terms of simplification, I have an R in both terms here, I have an R here, so alpha becomes T1, which is 12 newtons, minus T2, which is 10 newtons, divided by 1/2 the mass of the disk, which is 0.8 kilograms, times the radius of the cylinder, which is 0.3 meters. So we'll go ahead and calculate that up. And we get an angular acceleration of 16.67 radians per second squared. Whoop, sliding off the sheet there. Okay? So, brief recap. Pulley problems when the pulley has mass. We got to account for a differential in forces of tensions on either side. There has to be a differential in order for us to have an angular acceleration if we have to account for the moment of inertia. We can also use the no-slip condition where the tangential acceleration is equal to r alpha to connect the linear properties of the acceleration of the rope to the angular properties of the rotation of that pulley. And usually the pulleys are treated as discs where the moment of inertia about the center of that pulley will be 1/2 mass of the pulley times its radius squared.